Imagine holding a flashlight. Click it on, and in that same instant, the beam has already crossed 1,000 miles of empty sky. Light is so fast, so incomprehensibly, ludicrously fast, that our minds simply aren't built to track it. And yet, for the most ambitious dream our species has ever dared to chase, the dream of reaching the stars, even that speed isn't enough, not even close. Here is what should stop you cold. A beam of light leaving the nearest star beyond our sun today, this very moment, won't reach Earth until the year 2030. Over 4 years of traveling at the fastest speed the universe allows, just across the smallest gap in our cosmic neighborhood. Now imagine trying to make that journey in a rocket, something built by human hands, fueled by human ingenuity. The math doesn't just look bad, it looks like a locked door with no key. But in April 2024, a small research team in New York published a paper that made physicists around the world lean forward in their chairs. They had found something hidden deep inside the mathematics of general relativity, a solution, not science fiction, not wishful thinking, a legitimate, peer-reviewed, equation-satisfying solution to one of the most profound engineering problems our species has ever faced. A way to move through space that doesn't require breaking the speed of light, because it doesn't need to. What they found might be the first real crack in a door everyone had assumed was welded permanently shut. If physics discoveries like this give you that electric, slightly unsettled feeling in your chest, the one that whispers the universe is stranger than we thought, you're in the right place. We go deeper every week. Let's start with the scale of the problem, because until you feel it in your bones, nothing else will land the way it should. The nearest star beyond our sun is called Proxima Centauri. It's a small red dwarf, quiet and dim, burning at a fraction of our sun's brightness, tucked into the constellation Centaurus and visible from the southern hemisphere. Our closest stellar neighbor in the entire Milky Way galaxy. The distance, 25 trillion miles. 25 with 12 zeros behind it. Our brains didn't evolve to handle numbers like that. We evolved to judge distances between trees, between watering holes, between competing tribes on a savanna. So let's translate. Light travels at 186,000 miles every single second, fast enough to circle the entire Earth more than 7 times in a single heartbeat. In the time it takes you to snap your fingers, a photon could race from New York to Tokyo and back again. Nothing in nature moves faster than light. Not particles, not energy, not information. The speed of light is the universe's ultimate speed limit, built into the fabric of reality itself. And even at that incomprehensible velocity, light takes 4 years and 3 months to reach Proxima Centauri from our sun. Think about that. A beam of light leaving Proxima Centauri today, right now, this instant, won't arrive at Earth until sometime in the year 2030. That's the scale of the problem. Not 4 years to cross the galaxy, 4 years to reach the star right next door. Now consider what we've actually built. Voyager 1, launched September 5, 1977, from Cape Canaveral, Florida, is one of the most extraordinary objects our species has ever created. Nearly 50 years it has been traveling through space. In August 2012, it crossed the heliopause, the boundary where the sun's solar wind gives way to the interstellar medium, becoming the first human-made object to enter the space between the stars. It is still out there right now, still operational, still transmitting data home across billions of miles of cold, empty void, and it moves fast. Voyager 1 travels at approximately 38,000 miles per hour relative to our sun, 19 times faster than a speeding bullet, fast enough to reach the moon in under 7 hours, fast enough to reach Mars in a matter of weeks during a close approach. By every measure that makes sense in a human life, Voyager is screaming through space. Plug that speed into the equation for reaching Proxima Centauri, and the answer comes back. 70,000 years. Let that breathe for a moment. When Voyager 1 finally approached Proxima Centauri, if it were even aimed in that direction, the civilization that launched it would be unrecognizable. Humanity as we understand it today, our languages, our cities, our governments, our entire recorded history, would be archaeological sediment beneath whatever came next. And that's just the nearest star. Sirius, the brightest light in our night sky, sits 8.6 light-years away, 150,000 years at Voyager's speed. Betelgeuse, burning at Orion's shoulder, is 550 light-years distant. A probe heading there wouldn't arrive before our own sun had exhausted its hydrogen fuel and begun swallowing the inner planets, Earth included. The conclusion is brutal and unavoidable. You cannot inch your way to the stars. The deeper problem isn't engine power, it's physics itself, specifically what engineers grimly call the tyranny of the rocket equation. Every rocket ever built works the same way. Carry fuel, burn it, use the exhaust for thrust. But fuel has mass. That mass must be accelerated along with everything else, which means you need more fuel to push the fuel, which adds more mass, which requires even more fuel to accelerate it. The relationship is exponential, not linear. It spirals upward, devouring itself. The Saturn V rocket that carried Apollo astronauts to the moon burned through 3 million kilograms of kerosene and liquid oxygen in the first stage alone. All of it consumed in 2.5 minutes, just to push a tiny capsule containing 3 human beings 250,000 miles to the moon. Now scale that ambition to Proxima Centauri 100 million times farther. The calculation says you'd need more hydrocarbons than exist on Earth. More than you could mine from every oil field, every gas reserve, every organic compound on the planet. You'd need to harvest the atmospheres of Jupiter and Saturn, strip every asteroid and comet in the solar system of its organic molecules, and even then, the numbers wouldn't work. The rocket equation doesn't care how much fuel you have, it cares about the ratio between fuel mass and payload mass. And for interstellar travel with chemical propulsion, that ratio explodes beyond all reason. Engineers have known this since the 1950s. Every serious proposal for interstellar travel has tried to escape chemical propulsion entirely. Nuclear pulse propulsion, developed under Project Orion by detonating nuclear bombs behind a massive spacecraft and riding the shockwave, could theoretically reach a few percent of light speed. At 3%, the trip to Proxima Centauri shrinks from 70,000 years to 140. Still longer than a human lifetime, but within the scope of a generational mission. The practical obstacles, thousands of nuclear warheads, staggering radiation shielding, and the extraordinary political difficulty of launching a nuclear bomb-powered spacecraft from Earth have kept it firmly theoretical. Fusion propulsion would burn hydrogen the way stars do, fusing light elements into heavier ones and extracting the energy released. But we haven't mastered controlled fusion, even for stationary power plants on Earth. Antimatter propulsion would convert 100% of mass into pure energy via Einstein's E equals mc squared, the theoretical ceiling of efficiency, but every atom of antimatter must be manufactured in particle accelerators at enormous energy cost. Current production rates measure in billionths of a gram per year, and storing antimatter without it touching ordinary matter and exploding is an unsolved engineering challenge. Solar sails using pressure from light or powerful lasers could push gram-scale probes to 20% of light speed. The Breakthrough Starshot initiative, funded by Yuri Milner and supported by scientists including Stephen Hawking before his death, proposed exactly this. It might work for tiny unmanned probes, but a sail large enough to carry humans would need to span hundreds of miles. Each approach claws closer. Each represents genuine progress, but none of them cracks the real ceiling. That ceiling is the speed of light. In 1905, Einstein proved mathematically that nothing with mass can be accelerated to that speed. As you approach it, effective mass increases without limit. At 99% of light speed, a ship's apparent mass has grown by a factor of 7. At 99.9%, by a factor of 22. To actually reach light speed would require infinite energy. Infinite energy doesn't exist. This isn't a technological barrier. You can't solve it with better materials or more powerful engines. It's woven into the geometry of the universe itself, the absolute maximum rate at which causality can propagate between any 2 points in the cosmos. Or so everyone believed, until a young physicist in Wales decided to treat the problem like a homework assignment. In 1994, Miguel Alcubierre was a 28-year-old theoretical physicist at the University of Wales in Cardiff. Trained at the National Autonomous University of Mexico and doing postdoctoral work in Europe. He was, by his own admission, a fan of Star Trek, a show that had never explained how its faster-than-light warp drive worked, and which most physicists dismissed as pure fantasy. Alcubierre decided to ask the equations instead. He sat down with Einstein's field equations, the mathematical bedrock of general relativity, and asked them a precise question. What shape would spacetime need to have for a bubble within it to move faster than light, without any object inside that bubble exceeding light speed locally? Alcubierre had spotted a loophole no one had seriously pursued. Einstein's speed limit applies to objects moving through space. It says nothing about space itself moving, and there is a profound difference. We know space can move faster than light because we watch it happen. The universe is expanding. At roughly 14 billion light-years distance, galaxies recede from us faster than light itself. Not because the galaxies are flying through space at superluminal velocities, but because the space between us is stretching. It's like ants on a rubber sheet. Pull the sheet apart and the ants separate, not because they're walking away from each other, but because the ground beneath them is growing. This phenomenon is called metric expansion, confirmed by decades of astronomical observation, and there is no speed limit on it whatsoever. Space itself can move as fast as physics demands. Alcubierre asked the obvious question: if space can carry galaxies apart at faster than light speeds, could it carry a spacecraft? He constructed a new spacetime metric describing a bubble. Inside the bubble, spacetime is flat and completely normal. Time ticks at standard rates, light moves at standard speed. An astronaut inside feels nothing unusual. No forces, no acceleration, no sense of motion whatsoever. Outside the bubble, space-time is also flat, matching the rest of the universe. But at the bubble's boundary, something extraordinary happens. At the leading edge, space contracts sharply. Distances in front of the bubble compress. At the trailing edge, space expands just as sharply. Distances behind the bubble stretch out. The bubble rides forward on this geometry at any speed you specify, faster than light, slower than light, whatever you choose. From outside, an observer watches the bubble crossing space at superluminal velocities. From inside, the ship isn't moving at all. The pocket of flat space-time it sits in simply relocates itself, carried by the reshaping universe around it. The crew isn't accelerating. They're surfing a wave in the geometry of space itself. Alcubierre published this result in May 1994 in the journal Classical and Quantum Gravity. The math was correct, a valid solution to Einstein's field equations, not a trick, not an error, genuine geometry where a bubble could move faster than light without violating relativity locally. Inside the bubble, light always moved at light speed, outside the same. Nothing was traveling through space faster than light, but the bubble as a whole could cross interstellar distances faster than any light beam following the normal route. The physics community reacted with immediate excitement and an immediate problem. To actually build the bubble, you needed exotic matter, matter with negative energy density. Ordinary matter, rocks, gas clouds, the air around you, has positive energy. Positive energy curves space-time inward. That inward curvature is what we call gravity, mass attracting mass. Negative energy would do the opposite, curving space-time outward, creating a repulsive effect. Anti-gravity. You've never seen an object fall upward, never encountered a substance that pushes other things away gravitationally, because negative energy is simply not part of the everyday material inventory of the universe. And the early calculations for how much you'd need were catastrophic. Exotic matter equivalent to the mass of the entire observable universe. Every star, every galaxy, every particle of dust in every direction out to the cosmic horizon. The number was so enormous that many researchers assumed they'd made an error. They hadn't. Then came the refinements. In 1999, physicist Chris Van Broek at the Free University of Brussels exploited a strange feature of curved space-time. Interior volume and exterior size can be decoupled by curvature. In flat, ordinary space, a box that looks 1 meter wide on the outside contains 1 meter of space on the inside. In curved space-time, that relationship can break completely. Van Broek proposed shrinking the bubble's exterior to the size of an atomic nucleus, roughly 10 to the power of minus 15 meters, comparable to the diameter of a proton, while maintaining a normal-sized interior region through curvature. From the outside, the bubble would be microscopic and invisible. From the inside, there'd be plenty of room for a ship and crew. This geometric trick reduced the exotic matter requirement by more than 20 orders of magnitude, from the mass of the observable universe down to something closer to the mass of Jupiter. Still impossible, but impossibly closer to possible. In 2011, NASA physicist Harold White at the Eagle Works Advanced Propulsion Physics Laboratory took the problem further still. He proposed widening the bubble wall from a thin shell to a thick, gradual transition zone, and reshaping the bubble from a sphere into a torus, a donut, with the spacecraft riding through the center hole. The toroidal geometry concentrated the spacetime warping in specific regions and left others relatively flat, reducing the integrated energy cost across the entire structure. When White ran the numbers, the exotic matter requirement dropped to roughly 700 kilograms, the mass of a large motorcycle. Still an impossible substance, but the problem had shifted from requiring all the matter in the universe to requiring a room-sized amount of a substance we haven't found. White also proposed a tabletop laser interferometer experiment, similar in principle to the instruments that would later detect gravitational waves at LIGO, that might detect microscale space-time warping around specially arranged high-voltage capacitor rings. His team built and ran the experiment, getting ambiguous results that were suggestive but not conclusive. The fact that NASA was funding this work at all gave the field a legitimacy it had never enjoyed. Graduate students could study warp metrics without professional stigma. Papers appeared in mainstream physics journals. The field was starting to mature into something scientists could take seriously. Then a small private research group in Manhattan entered the story with a fundamentally different approach. Applied Physics, headquartered at 477 Madison Avenue in Midtown Manhattan, was founded by engineer and entrepreneur Gianni Martire with a simple mandate: treat warp drive not as a theoretical curiosity, but as a systematic engineering problem. Map the solution space, build the tools to evaluate candidate designs, eventually construct hardware. The team is small, under a dozen core researchers, but serious. They hold PhDs from respected institutions, publish in peer-reviewed journals, and attend conferences alongside academic physicists. In February 2021, two team members, theoretical physicist Alexei Bobrik and Gianni Martire, published a landmark paper titled Introducing Physical Warp Drives. Rather than proposing yet another specific design, they created a general framework for classifying every possible warp drive geometry that could exist. Their core insight was elegant. Every warp drive, without exception, consists of three regions. First, a flat outer region far from the ship, ordinary space matching the vacuum of the universe. Second, a flat passenger region at the center where the crew lives and physics behaves normally. Third, a warping shell in between that does all the work, creating the compression ahead and expansion behind. Every design ever proposed, from Alcubierre's original to Van den Broek's shrunken bubble to White's torus, fits this three-region structure. The differences between designs come down to how the warping region is shaped, what kind of matter fills it, how thick it is, and how it interfaces with the surrounding universe. By mapping the entire landscape this way, Bobrik and Martire could ask systematic questions about what had been explored and what hadn't. They found that almost all previous research had focused obsessively on superluminal designs, faster than light, because that was the headline goal. Subluminal warp drives, bubbles moving below light speed, had been almost entirely ignored. And subluminal drives, they pointed out, might satisfy the energy conditions that exotic matter violates. They might not require negative energy at all, and they would still be extraordinary. A warp bubble at 90% of light speed crosses the solar system in hours and reaches Proxima Centauri in under 5 years, delivering the crew without a single G-force of discomfort. The Bobrik-Martire framework became the standard reference going forward. The field had been classified. Now it needed a solution. In 2024, the Applied Physics team delivered one. Classical and Quantum Gravity, Volume 41, Number 9, Article 095013, published April 29, 2024. Lead author Jared Fuchs, with co-authors Christopher Helmerich, Alexei Bobrik, Luke Sellers, and Gianni Martire. Title: Constant Velocity Physical Warp Drive Solution. What the paper claimed was genuinely extraordinary. The authors presented a warp drive solution satisfying all of the classical energy conditions. All of them. The weak energy condition, the null energy condition, the dominant energy condition, the strong energy condition. These aren't arbitrary rules. They emerge from quantum field theory and have been tested against countless observations. Violating them means dealing with something unphysical, something the universe simply refuses to produce. The Fuchs warp drive violates none of them. The design combines two elements. First, a stable matter shell with a specific density distribution built entirely from ordinary positive energy material, protons, neutrons, electrons, arranged in precise geometric configurations, nothing exotic, nothing requiring new physics. Second, a mathematical feature of the spacetime metric called a shift vector distribution, which describes how different parts of space move relative to each other. In the Fuchs design, the shift vector creates a flow pattern that mimics the Alcubierre geometry. Space compresses slightly ahead of the bubble, expands slightly behind, but this compression and expansion are driven entirely by ordinary matter in the shell interacting with the shift vector structure. Together, they produce a genuine warp effect. A region of flat space moves through the surrounding universe, carrying everything inside it along for the ride. The team evaluated the design using software called Warp Factory, which they developed and released publicly. When you run the Fuchs metric through it, the visualization shows blue everywhere. Blue means positive energy density, ordinary matter, the kind that makes up stars and planets and you. Red would indicate a violation, a region demanding exotic matter. The Fuchs warp drive has no red anywhere. It is entirely blue, entirely physical, entirely consistent with the universe as we actually find it. As Fuchs explained in interviews, prior warp drive models required matter and energy content that was unphysical, features nobody has ever observed in nature. The new approach avoided that by incorporating only positive energy, phenomena like light, ordinary matter, and antimatter, all of which exist naturally, all of which we can detect, measure, and in some cases produce. For the first time since Alcubierre's original paper 30 years earlier, a warp drive design existed that didn't require anything the universe refuses to provide. The physics community responded with cautious optimism. The solution was mathematically valid. The energy conditions were genuinely satisfied. It was real progress. Skeptics correctly noted that the Fuchs design is explicitly subluminal. It does not enable faster-than-light travel. The bubble moves at constant velocity below the speed of light. But here is what that means in practice. A warp bubble at 90% of light speed would reach Proxima Centauri in about 4.7 years, as measured by outside observers. For the crew inside, time dilation would shorten the subjective experience to roughly 2 years. That's a long voyage, but it's one a single astronaut could make within a working lifetime and return from. More importantly, a subluminal warp drive transforms travel within the solar system entirely. Mars currently takes 6 to 9 months in a slow, fuel-constrained arc governed by orbital mechanics, with launch windows opening only every 26 months. A warp ship could accelerate continuously, push to a significant fraction of light speed, and compress the entire Mars journey into days. Jupiter, currently a multi-year expedition, becomes a matter of weeks. Saturn, Neptune, the Kuiper Belt, all within reach of short-duration crewed missions. The geography of the solar system collapses into something navigable within a human career. The crew arrives fresh throughout, unaffected by any acceleration forces, because inside the bubble, space-time is flat. They feel nothing while the universe rearranges itself around them. And there's one more advantage most coverage misses entirely. When a warp bubble exceeds light speed, the leading edge races away from the ship's interior faster than any signal can follow, creating what physicists call a causal horizon. Horizons are dangerous. They generate Hawking radiation, potentially intense enough to irradiate the crew, prevent steering because the pilot loses causal contact with the ship's own front wall, and cause a devastating release of accumulated interstellar particles when the bubble shuts down. A 2012 paper by physicists McMoneagle, Lewis, and O'Byrne showed that even the extremely low density of interstellar space, accumulated over light years of travel, produces a catastrophically energetic beam at the destination, enough to sterilize an entire star system. A subluminal bubble creates no horizon whatsoever. None of these consequences apply. The physics permits it. The materials are ordinary. The crew is protected. And for the first time, there exists an actual engineering path connecting our current knowledge to eventual warp capability.